Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
See a few faces who are here yesterday. I'd like to thank Thorsten again for flying out from Ithaca, number one, and number two, giving two talks on pretty diverse topics. So yesterday he spoke about a lot of user eye tracking and behavioral data that he's used to estimate and improve ranking functions. Today he's going to talk about work that I think is a little bit more in his, and he gave a great talk yesterday. The room was packed, and he spent all afternoon talking to folks interested in various aspects of understanding human web search behavior. Today he's going to talk, I think, about something that we associate more with him, a little bit more in his comfort zone, perhaps, on learning structured outputs for support vector machines.
Cool. Thank you, Sue. Thanks for the second introduction in 2 days. So yesterday was all about how to get training data that we can use for machine learning. And today it's actually the opposite. I don't care about training data. I just care about the algorithms. And it's different applications, actually. So this joint work with people from Brown, Thomas Hoffman, Yanis Sohantaridis, and Yasmin Altoun, and people from Cornell on various applications. Tom Finley, one of my PhD students. Ron Elber, we're doing work on protein folding. Phil Segoris, work also on protein folding. And Dan Fleischer, work on part-of-speech tagging. So if you hear about these different applications, they sound very diverse, but I think they're kind of tied together by one theme, and I hope this theme is going to become clear during this talk. Okay, so this talk is going to be about supervised learning. So very straightforward. We want to learn a function h, and this function is a mapping from some input space x to some prediction y. And I mean, that's what we do in machine learning pretty much on a day-to-day basis. And we've gotten very sophisticated about methods for solving this problem. In particular, sophisticated about methods that can handle pretty complicated x's here. So for example, me personally, I've spent a lot of time doing text classification, where the x is a high-dimensional very high-dimensional vector. Well, but we've also gotten to learn how to classify sequences, for example. So, for example, gene sequences. Or even going beyond this, having big structural inputs here that we want to, for example, classify proteins or classify molecules in general. But what's common to most of these applications is that the y that we are predicting is just a single number. It's a univariate output. So, for example, in classification, we might just want to classify +1, -1, yes or no. Or we want to do regression and we predict a number. What I want to do in this talk is talk about problems where what we want to predict is not a univariate object, but a structured multivariate object. So if you want to think about this, I'm not going to care in this talk much about x, but I'm really going to care about the y's here. How can we learn more complex y's? So here are a couple of examples where I think this is an important problem. So if you think about natural language processing, natural language parsing, the problem that you're trying to solve here is essentially a supervised learning problem, or you can phrase it as a supervised learning problem. You're given a sentence x, and what you want to predict is the correct parse tree. So you have a y that consists of a tree. You want to predict a tree. And really, if you want to solve this problem, it becomes pretty hard to break this down, let's say, into a set of binary classification problems, right? You can't just kind of classify, oh, this should be a noun phrase, and this should be a noun phrase again, but there are all these dependencies, right? The whole thing has to eventually form a tree. And if you break it up into pieces, that consistency probably goes away if you're not careful. So you have a prediction problem where you want to predict the structured objects with lots of dependencies between the constituents, just that coming from the structure. Here's another example. For example, in text classification, what we often have is that we don't just have one classification problem, but we want to assign to a particular article a whole bunch of topics. So you can think about this as predicting a vector of +1 decisions. So is the article about Antarctica? Is it about oil? Is it about Iraq? Right? So we have a whole vector. And conceivably, again, splitting this up into just one binary classification task for each example might not really model the problem that well. It might help us if we took into account dependencies between these categories, and that might help improve our model. So, for example, correlations between these categories. So here we have a prediction problem where we want to predict a vector. Again, with dependencies. It even comes up if you just think about binary classification, but you don't just want to minimize error rate, but you want to maximize some nonlinear multivariate loss function. So what people in text classification typically care about is not the error rate of your classifier, but the F1 score of the classifier. And the F1 score is this funny nonlinear combination of precision and recall. Now, the complicated thing about F1 score is that really what it does, it makes your predictions dependent among each other. So even if I have pretty much perfect knowledge about a particular example, so for example, I have a new example vector x8 here, and I want to decide whether I should classify this new example as positive or negative for some binary classification task. And let's assume that I have perfect knowledge of this distribution here. So I know the probability that this example is a positive example is exactly 0.4. If I want to maximize F1 score, I could not decide whether I should actually classify this example as positive or negative. If I want to minimize error rate, clearly I would want to classify it as negative. But for F1 score, that doesn't work. And the reason is because we have this nonlinear combination, it actually matters what the probabilities of the other examples are. So again, we might want to think about this problem as, given the set of examples, we actually want to make a vector of predictions where we have dependencies between the examples. And my final example, I'm going to come back to this later in the talk. And the final example is a problem that I'm working on with Thomas Finley. So the noun phrase coreference problem. So you're given a document here. And let's say somebody marked all the noun phrases in the document. And what your task is to group these noun phrases together by whether they refer to the same entity. So for example, here are the policeman and these two he's here all refer to the same entity, though you want to cluster them together. So what you have here is essentially you have a clustering problem where you're given a set of items and you want to cluster, or noun phrases, and you want to cluster them together by whether they refer to the same entity or not. Again, we have this XY problem, X set of noun phrases, Y, we want to predict what's the correct clustering. So all of these problems have the same structure, right? We have an input X and a complex multivariate output Y. So here the output has to form an equivalence relation, a clustering. And for all of these problems, we potentially have supervised training data. So for example, there are repositories of data where we know what is the correct clustering for a particular document. What I want to do in this talk is I want to present a method that we can use to tackle all of these problems. And it's going to be a somewhat fairly general SVM approach to this problem that we're going to apply to all these examples that I gave, and I think applies to a lot more as well. So what I want to do in this talk is first talk a little bit more. I mean, I've talked a little bit already about the research questions and point you to some related work, and then talk about this algorithm for learning these complex structured outputs. After the general introduction, I want to talk about 3 examples that we've tackled with this algorithm and give you some experimental results for those. Okay. So why do we need methods for doing these predictions? So for predicting complex outputs? Well, one reason is there are a few applications where we don't actually have methods for solving these problems. So for example, for this coreference, noun-phrase coreference problem, what people are currently doing is essentially a two-step approach. They're first trying to do like a pairwise classification between noun phrases, trying to figure out are they coreferent, should they be in the same cluster or not, coming up with these n-squared binary decisions, and then trying to do some post-processing to actually make them an equivalence relationship, right, and break inconsistencies. But presumably, this two-step approach, it's somewhat harder to handle, and you're not really, well, since you're not doing it in one step, it's really hard to really optimize the performance or the particular criterion that you want. Second reason, for many other applications, like let's say for parsing, of course we have methods for doing this already, like probabilistic context-free grammars. But most of these methods are generative models. And I'm going to talk a little bit more about generative models when we do the comparisons. So what generative models do is, how you can think about generative models learn the joint distribution of the x and y, where discriminative models learn just the conditional distribution of the y's given the x. So if you want to think about, let's say, natural language parsing, a probabilistic context-free grammar as a generative model, and the kinds of models that we're going to learn here with these methods as discriminative models, it's kind of like comparing, it's actually a very close analogy of naive Bayes classification for text classification and support vector machines for text classification. So like a probabilistic context-free grammar, you can think about as the naive Bayes equivalent of grammars. So you're making lots of independence assumptions and then estimating this joint distribution. Now, what we know from text classification is that in many situations, SVMs quite substantially outperform generative methods like naive Bayes. And if you look across the most common benchmarks that people use in text classification, there's typically quite a substantial difference between the two. So presumably, by moving from a generative model for structured output prediction to a discriminative model for structured output prediction, we might see similar gains. You had a question?
People have showed that you can train applications
Well, then you would call it not naive Bayes anymore. Right. And exactly, I fully agree with what you're saying. So naive Bayes is essentially learning a linear classifier, right? And there are tons of ways of learning, coming up with the parameters of a linear classifier. Naive Bayes is one way of coming up with a linear classifier. A linear SVM is a different one. Conditional likelihood, maximum entropy models would be other ways of coming up with these methods. But I wouldn't call it naive Bayes then anymore, right? So what's kind of interesting about this comparison is that both naive Bayes and, let's say, a linear SVM learn exactly the same type of model. They're linear models over exactly the same attributes. And still you see quite a performance difference. So one thing that often makes these generative models hard to handle is that we have to account for these independence assumptions. And that it's somewhat restrictive in what we can express in these models. So moving to discriminative models gives us more flexibility in what kind of features we can express and what kind of information we can put in our model. And we can, for example, use things like kernels that people have come up with for for support vector machines to get richer models. And finally, presumably, what we have learned for classification and regression for these discriminative models, we might be able to transfer to the structured output prediction models as well. So let's look at some related work. I don't want to talk about generative training. Has a long history, and you probably all know about hidden Markov models or observable Markov models, how they're typically called in natural language processing application, probabilistic context-free grammars, Markov random fields. For discriminative training, again, for similar models, or for actually models of the same type, people have come up, of the same form, people have come up with different ways, as you've said, for training them. And so one way of doing discriminative training, for example, in statistics, is looking at multivariate output regression. So there the problem is that you're predicting a vector of real variables where you have dependencies between the random variables in these vectors. Similar to that, but taking these ideas and applying them to not just predicting real vectors, but predicting structures, is what Weston and all call kernel dependency estimation. What you do there is you first take, if you have a structured input, like a sequence, and you want to predict a tree, which is, again, a structured output, what they do, they come up with a way of first mapping the sequence into real space, then doing a prediction in another real space, and then computing an inverse mapping back to the tree. In many situations, this can be done efficiently, but often the inverse problem is actually quite hard. Directly training things like structured models, like a hidden Markov model, in a discriminative way, I think this is the first reference I could find. And that was, along these lines, refined and more generalized in conditional random fields by Lafferty and others. There, the idea is that you take a model of the same form as a generative model, like a Markov random field, but you train it in a conditional fashion. This was one of the kind of, at least in the machine learning community, the Lafferty paper, one of the kind of the key methods that I think made many people realize that you can actually do the structured output prediction in an efficient way. And to some extent, the models that I'm going to talk about have a lot of similarity to the conditional random fields models in their structure, but not in terms of how they are trained. And in particular, there are going to be examples where training a conditional random field model is not tractable, but training a support vector model is tractable. An approach doing structured output prediction for transducers, finite state transducers, Jan LeCun proposed. So you would essentially learn the parameters of this transducer with a neural net, but you run into the same problems of having local optima in these problems, which we are not going to run into. One of the foundations for the work that I'm presenting goes back to Michael Collins' recent paper on perceptron training for hidden Markov models. So he essentially learns a model of the same type here, but trains it with a rule that doesn't require that you compute the partition function. And in parallel to us, Taskar and others came up with a similar formulation of the problem, but very different algorithm for solving the problem in terms of support vector machines. Ours is more general in terms of the loss function that you can use. OK, so let's think about the problem that we're trying to solve here. So we want to make a prediction, let's say, and I'm going to use this problem of natural language parsing as a running example here. We want to make a prediction that goes from a sequence to the correct parse tree. Now, one way we could view this problem conceptually is that what we want to do is a multi-class classification problem. We would just have one class for every possible tree that we can form over the sequence with our grammar. And then the prediction that we're doing is predict the correct tree. Now, conceptually, this might work, but there are a couple of problems with that. First, there are exponentially many trees over that sequence. So essentially, you have a multi-class classification problem that has exponentially many classes. So you have to worry about how to pick the correct class if you have exponentially many classes. And even more, how do you learn such a model if you have exponentially many classes? And related to that is, well, if you have exponentially many classes, if you just have one parameter for every class, you're going to have exponentially many parameters, and you run into statistical problems, not just efficiency problems. So, well, these might look a little daunting, but actually what we're going to see is that you can overcome these problems. Okay, so here's the algorithm that we propose for this problem. So it's based on Vapnik's support vector machine. And let me give you the one-slide introduction to SVMs just for the basic problem of binary classification. And then we're going to extend this formulation to structured output prediction. Okay, so in binary classification, what you have is you have training examples which are x, y pairs. The x's are feature vectors. The y's are just +1, -1. And what an SVM learns is a linear function that, if the data is linearly separable, separates the positive from the negative examples, and at the same time finds the hyperplane that maximizes the distance to the closest training examples. So you can think about this as finding a separation, green here, that makes the gray area, the two parallel plates here, as far apart as possible. And this distance is called the margin. I'm going to note it by delta here. If the data is not separable, which it typically is, then you would introduce slack variable psi i's here. And you would optimize the size of the margin. You want to make this as large as possible. And you want to make the slack variables as small as possible. And you want to trade off the two. These slack variables measure the distance normalized by the margin size that an example is away from the correct side of the margin boundary. So this example is way past the margin boundary. And the slack variables are scaled so that a slack variable is greater than 1 exactly when an example is on the wrong side of the classification boundary. So this one here would probably have a value of 2.5. It's 2.5 times the distance here. This one has a value that's between 0 and 1. So the slack variable is non-zero, but it's less than 1. The example is still on the correct side of the hyperplane. What a support vector machine then optimizes is a trade-off between the size of the margin squared, delta here, and the sum of the slack variables with some trade-off constant c that you have to set via cross-validation. Turns out that this quantity, the sum of the slack variables, if you think about it, it's pretty clear this is an upper bound on the number of training errors. If you want to actually find this hyperplane, what you need to do is you have to solve, for example, this optimization problem. And what you have here is for every example, you have one linear constraint that essentially says, is the example on the correct side of the hyperplane? And you see the slack variable is greater than 1 if it's not. And then you optimize this objective. The sum of the slack variable, the size of the margin is essentially encoded here by the norm of the weight vector, and the sum of the slack variables is here. And you have this trade-off constancy. So this is a convex quadratic program, and they're an efficient way of solving it. Also, interesting ways for SVMs to extend this to nonlinear classification rules. You can always express the final weight vector that you're trying to learn here as a linear combination of the training examples, which lets you use these kernels and learn nonlinear classification rules. Okay, so how are we going to take this and turn it into something that can predict trees? Now, we said we wanted to treat this problem as a multi-class classification problem. And we have as inputs the sequence of words, and our classes are the trees, all possible trees. Now, there is an approach for doing multi-class classification with SVMs. And one of the approaches goes back to Kramer and Singer. And while we can't apply this directly, let's take a look at it, and maybe we can extend it in a way that is suitable for our problem. So here's the multi-class SVM by Kramer and Singer. So what they're doing is they're not learning just one weight vector, but they're learning one weight vector for every class. Our training data now is feature vector X and a label Y. And the label is now not just +1, -1, but it's the number 1 to k, right, indicating the class. So when you want to make a prediction, what the multi-class SVM does is it computes the inner product, so a linear function again, between each of the weight vector for each class with the example that you want to classify, and then it predicts the class that has the highest value. So you can think about this as a ranking problem. So applied to our task, we would have all the trees here. We would have one weight vector for every tree. And we would have a feature vector that somehow describes the tree. And then we would compute all these inner products here. We would rank the different trees, and we would pick the tree that has the highest value. And that would be our prediction. If you want to train such a ranking, as such a multi-class SVM, again, this can be written as a convex quadratic program. Essentially what you're saying is, well, find me a small norm not only of the one weight vector, but a small norm of all the weight vectors. So that would be the first sum in the objective function there. Again, we have a sum of the slack variables that measure the training error. And then essentially for every class here, we would say the correct class for this example has to have a higher output, a higher value than all the incorrect classes. And you can, again, encode this as these linear constraints. And you add a slack variable there. So for every example, you get a set of linear constraints that says the correct example has to have a higher value than, the correct class has to have a higher value than all the incorrect classes. Mm-hmm. Yes, there is still. And intuitively, the margin now is the distance between the highest scoring and the next that follows up. It's not that geometric anymore. Yes, I agree. Yeah, feel free to ask questions when anything's unclear. So, okay. So this gives us a starting point, but we have these three problems in our particular application here, right? Since we have exponentially many classes, we have to worry about how do we make the prediction efficiently. Clearly, if we have to do some computation for each class, this is not going to scale, right? Then we have to worry about how do we do the learning efficiently. And we have to worry about how do we get a manageable number of features, a manageable number of parameters, right? If you have just one parameter vector for every possible tree, that's just going to be way too big. Mm-hmm. I think I didn't catch everything acoustically.
When I have a classification problem, I just have a vocabulary for what my classes are.
Mm-hmm.
And that's fixed and independent of the
Mm-hmm.
Now, here for parsing, that doesn't seem to be the case.
So the classes could actually change for different inputs, right?
Classes that I need to disambiguate when aren't impact the function of the
That's true. I mean, you could you could stretch it a little bit by saying, okay, it's all possible trees. My classes are all possible trees over all possible sequences. It gives you an even bigger space. Doesn't exactly help, I agree. I don't think this is going to, it's going to turn out not to be the key problem, that there is this dependency that kind of the reasonable classes depend on the input already. That's actually going to turn out to not be a problem. Okay, so let's first look at the last problem here. How do we get this into a representation that has a somewhat manageable number of features? So we're just going to, at this point, just do a little notational trick. Instead of having one weight vector for every class, we're going to introduce a feature vector that describes the match between the input and the output that has a fixed dimensionality. So if you went to my talk yesterday, this is actually the same as we had for matching queries and documents, right? So you can think about this feature vector phi here as a set of features that describes the match between this sequence and, let's say, this tree. That would be the set of features here. And we're going to think about how we can construct these features in just a second. What this means, though, is that instead of having a kind of a variable number of w's, one for each class, we just have one w. And what varies is really just the feature vector that matches the tree to the input. Now, if we want to do prediction, what it comes down to now is that we want to compute the argmax over all possible trees that maximizes this linear function. Okay, so at least in this notation, we've fixed the last problem. We have a manageable number of features. We might have created other problems.
Different length of the sentence, you have different classes. Potentially, the number of trees will be different if you enumerate all the possibilities. But how could tree be defined in such a way that you could fix number of times?
So you could, for example, have a match between this tree. Well, so one thing you could just define it that the tree size has to match the input sequence size. And that's effectively what's going to happen here. But you could just define it in a different way that you would say, OK, if these two don't match in size, there's going to be a feature in here that is on. And then we would, for example, learn a weight that says they don't match in length. And presumably, the support vector machine would learn if they don't match in length, this can't be the correct tree to predict.
But first of all, do we have to decide the total number of passes?
No, we don't. So this y here, it turns out that it's not really crucial how to define. I mean, it's going to be defined implicitly later. Yeah.
I've actually been thinking about how you would discriminatively train PFG. And so, and the way I've been thinking about it, the features would be the number of occurrences of each local tree, or CFG rule. Would that be an instance of your feed?
Yeah, that's going to be.
So then the number of feeds would be equal to the number of CFG rules in the game.
That's exactly right. And that's what the slide essentially says. Thanks for the transition. So here's it's actually only one way you can do it.
Right,
One thing.
That's only one possible way.
Yeah. So what you have in the PCFG is you have these rules, right? Sentence goes to noun phrase, verb phrase. And with each rule, you have a number attached. So in a PCFG, this would be a probability. If you take a log of this probability, so what you do in a PCFG is then you want to find the tree that has the highest probability, and you make independence assumption just like in naive Bayes. You say, OK, all of these probabilities of individual rules occurring are independent. Let's just multiply all of them. And that's the probability of a tree. Now, if you take not the probabilities and multiply, but you take logs of everything, what essentially happens is that you get a linear function, right? So then if you want to find the tree that has the highest probability, you would solve this argmax problem. These W's here would be the log probability. And the phis here would be the histogram of how often did a rule occur in the tree, just like you said, right? So essentially, one particularly simple way of defining this vector, and very convenient one, and as it turns out, defining this feature vector phi here for the match between a sentence and a tree is exactly via this probabilistic context-free grammar. So we would just count how often does the rule sentence goes to noun phrase, verb phrase occur in this tree. Occurs once. This one occurs 0. This one occurs twice. So you essentially just get a histogram of the rule occurrences here. Now, if you write it this way, you have something that's exactly has the same structure as a probabilistic context-free grammar. Well, the nice thing about picking this particular structure is that now you can solve this argmax problem efficiently, right? You can just use your CKY parser to find the tree that maximizes this function here. And you can do that in polynomial time. So what this gives us is an efficient method for inference, right? If you pick this particular phi, and if you pick this linear representation, we can solve the inference problem efficiently. So that solves our second problem. Turns out that this is not the only representation that we can pick, but we can pick actually much more general representation, much more powerful representation. I'm going to talk about that in a second. And I think that's one of the key advantages between a discriminative and a generative approach. So the last problem that we need to solve is how do we actually learn the weights now with a support vector machine efficiently. So for generative training, this can be done very efficiently. You just essentially count how often a rule conditionally occurs.
Question here. So if you could solve that problem in a general term, does it mean that you can automatically use the grammar rules compared to
Now, the particular setting that I'm so I assume that the rules are given in the training data. So I would just look at all the training data that I have. So training examples mapping X to Y. And I would collect all the rules that occur in the training data and call that my grammar. There might be rules that haven't occurred in the training data. Yeah, that's going to happen, but it's not going to make our algorithm look particularly good. But yeah.
So you have a means of computing the scalar for this particular guy. So of course you could iterate through all possible trees to compute that, but you're sneaking the component at one time.
Right.
There's some steps between them.
Oh, so the way of doing this efficiently is dynamic programming, like you would do in a parser.
So you kind of do kind of a halfway parsing to get most of your information, and then you still have some types of, I can use this as a cost vector in your GPL.
Yes, exactly.
Presumably, you can also do this with linear arithmetic, right?
Yeah.
So what makes the linear arithmetic? You say something, you have some problem which the linear arithmetic is not practical, but your method is practical.
So for parsing, it's actually, you could do that with a conditional random field too, I believe. What you need to do for a conditional random field is you need to compute the partition function when you do the training. And it turns out that you can avoid doing that here. And there are going to be problems where you can compute, essentially you can compute the argmax efficiently, but you couldn't compute the sum efficiently of this quantity. And for training a conditional random field, you have to be able to compute the sum. And you don't need to do this here. So, okay, so how do we do the training? So essentially what we have training data down here, X, Y pairs. And we want to tweak the w's so that the correct tree achieves the highest value in this linear function. And we want to do that over all training examples that we have. Well, we can write this again as a system of linear equations, essentially. Well, what we could write is the correct tree has to have a higher value in the linear function than all the incorrect trees. And if we want to have a margin, we add this +1 and normalize by the length of the weight vector. So it gives us the same margin analogy like we have for classification. And then we just have one set of constraints like this for every training example that we have. If we want to introduce allow training error, we can introduce a loss function, essentially measuring the distance by which this guy is lower than an incorrect label. And we would scale this by a loss function here. And then we would introduce it in the following way. Well, one way of doing this, there are actually two ways that we've explored, but I'm just going to talk about one here, is that we say, OK, the correct one has to be larger than all the incorrect ones by the loss that we would incur if the incorrect one was predicted was the prediction. So if you now if you then introduce the slack variables here, and again, look at the sum of the slack variables, if you stare at that for a minute, you can see that the sum of the slack variables, just like for classification, is an upper bound on the training loss. So what you're doing here, just like in classification, you're minimizing training loss and trying to have a large margin at the same time. And again, you have this trade-off constant C that you need to tune. So, but what I kind of glossed over so far is the problem that we have here. We're comparing the correct tree to every incorrect tree. So we actually have a huge set of constraints here, right? Linear constraints, it's a convex problem, but we have a huge set of constraints, right? It's exponential there's one constraint for every incorrect tree, so we have an exponential set of constraints. It turns out that despite the fact that this problem is huge, we can actually solve it in polynomial time with a very simple kind of cutting plane algorithm. And the algorithm is extremely simple, as you can see. So the basic idea of the algorithm is that you start with an empty set of constraints. And then you keep adding constraints as they are needed and as they are violated. So what you would do is you would first, so the algorithm goes in multiple iterations. And in each iteration, it would compute the constraint that is most violated. So this essentially comes down to computing this argmax. And as you can see, this argmax is almost the same as you would need when you do prediction. This gives you the constraint that's most violated. Then you would check whether this constraint is violated by more than some precision epsilon. Epsilon is the precision up to which you want to solve the problem, 10 to the minus 2 or 3 or something reasonable. If it's violated by more than epsilon, you add this constraint to your working set, and you would re-optimize, solve this quadratic program that you have over this subset of constraints. If you keep doing that, what you can show is that after adding only a polynomial number of constraints, you have solved your optimization problem up to the desired precision of epsilon. No, for simplicity, we just keep them in. It turns out we mostly keep them in because otherwise our proof wouldn't work. So I think you can probably get a little bit better. But it seems to be very efficient. You're going to see in the examples later, typically you end up with having with actually half of the constraint that you're adding being necessary constraints. So you could only gain a factor of 2. So here's, yeah.
The step optimized at the end, do you have a way of doing
Yeah, so we essentially start with the previous solution, and then there are probably smarter ways of doing it. But we start with the previous solution and do a gradient search from there. It's actually using SVM Lite, the quadratic programming algorithm SVM Lite to solve these.
Actually, I thought this is the same as multi-class SVM. The whole trick is that you turn the structure into a multi-class using the V matching. So why should I would be bigger than multi-class SVM?
Well, you could never implement this as a multi-class SVM because the problem is just way too big.
I think it's predetermined. Whenever you have a grammar, then you can input your fees here.
Yes.
So when fees, even then the problem will be identical to multi-class SVM. The one you showed earlier.
Right, but over your grammar, you still have an exponential number of classes, right? So you couldn't solve.
Scale. So it's a scale
It's
problem
it's
in terms of how many classes you have.
it's this. Yes, you can think about it.
It's nothing to do with the structure here.
No, well, in a sense, not. I mean, there's this translation step of taking a structured output, a structured prediction, and turning it into something that looks like a multi-class classification problem. But then you end up with these efficiency problems. Yeah. So what this algorithm does is essentially, so what we could show for this algorithm is that you never need to add more than this polynomial number of constraints before you terminate, and you find a solution that's epsilon close to the solution if you had considered all exponentially many constraints. And it's polynomial so this is the number of examples that you have. This is the trade-off parameter C here. This is a maximum on the loss function. And this is a bound on the norm of the feature vectors. So you can think about this as the maximum number of non-zero entries in each of the feature vectors. So the feature vectors can be very high dimensional, but if they're sparse, that's OK too. And epsilon here is the desired precision. Typically, what we're using is 10 to the minus 2 or something like that. That turns out to be sufficient in practice. OK, so we can predict efficiently, we can learn efficiently, and we have a model that has a concise number of features that doesn't kind of blow up exponentially. So one of the things that we've applied it to is natural language parsing. And so what I've done here is I've taken Mark Johnson's CKY parser. He has a very nice implementation on the web, very clean. It's not particularly fast, but very clean. And I've just integrated it into our algorithm to solve this argmax problem, and to also, these two argmax problems. And then I've done a comparison between a regular probabilistic context-free grammar as computed by Mark Johnson's code here, and a grammar that has exactly the same structure, but that's not trained generatively, but discriminatively with our SVM algorithm. One of the nice things that you can do now is you can actually say what the loss function is that you want to optimize. So typically people in natural language parsing don't care about error rate, like how many sentences do you get correct precisely, but they have an F1 score, kind of looking at what fraction of the nodes you get right in a particular way. So we trained this SVM now to optimize exactly the error measure that people use in natural language parsing. So this was trained on a subset of sentences that have length at most 10. One of the reasons for this is that the parser gets extremely slow if you have long sentences. And so that gives you roughly 4,000 examples for training and 163 examples for testing here. So, and despite the fact we see some similar effect that we see for naive Bayes for text classification, we see here too, despite the fact that we're training exactly the same model, the performance is the same structure of models, the performance actually goes up significantly here. So, I think partly this is due to the reason that we're avoiding independence assumptions that we're making here and that are not correct. And it's partly due to the fact that we're actually optimizing to the loss function that we really care about. That was a question.
That's what I was going to ask you. Which part do you think is making the most difference? If you test that again using
Yes, we did that too. What happened was, so this is accuracy, fraction of sentences that we get correct. What turned out, if you don't use the F1 loss here, but you use just number of sentences that you get correct, this number stays high, better than for the probabilistic context-free grammar. But this one is just 86 point something, so it's just marginally better. So I think actually the loss function makes a substantial difference here. Mm-hmm. Mm-hmm.
So just going back to the last slide, you started out with an exponential sequence. You have your algorithm where you're filling in the constraints in time, and the theory of that it takes less than a polynomial number, which is amazing. Just wondering, what is the little nugget that allows that feature?
Well, honestly, I don't really have a good intuition for why it's true. So, but it's definitely something I want to think more about.
So when you try to split out, you can look at the weight, and then compare it with the PCFG. Is there anything interesting there? Do you see certain rules that just badly multiply PCFG?
I haven't done it. I think it would be interesting. But the weights that they're learning are actually really different. So, for example, the SVM has no restriction of assigning positive or negative weights. So the SVM actually assigns positive weights. So I think the weights actually look very different. I don't know. Yeah. This is not lexicalized at all. Yes. So this is just my toy example. This is not a real.
Well, right, I understand, but there is sort of constant concern that we have here that we might be so far in the wrong step, and that a couple of points here is right.
Yes, but I think actually one of the key differences is, and that's going to be the next experiment, is that this gives you the opportunity to put features in which you would have a really hard time handling in a probabilistic context-free grammar. So, okay, before I go to that slide, let me just point out something. What you end up with for the training here is that you typically have to do 12 iterations, just to give you an idea of the training time, 12 iterations through this algorithm. You end up with 8,000 constraints that you're adding, and I think roughly half of those are ending up to be support vectors. And the training time is 4 hours, which compares a little unfavorably to the training time of the PCFG. But well, kind of like an SVM, so something super linearly. Mm-hmm.
Because the training time for that would be, based on my experience using electron for other tasks, seconds or at worst 6 minutes.
So,
4 hours.
right. So you.
So the slow part is parsing to get the additional sample. So with Paul, he has a step of with his current weight, parse those and add those things.
Oh, okay.
And which is also probably one of the slower steps here.
Yeah.
So what actually takes most of the time here is doing the parsing. I think it's more than 80% of the time. It's just doing the parsing. It's roughly. Well, it depends on how far you run it till you have it converge. If you actually want to have like a perceptron like a large margin perceptron, I think this is going to be faster.
I bet in accuracy.
Oh, in accuracy? Oh, okay. So we've done, I don't have the numbers here, but Thomas and Yannis have done experiments for named entity recognition, where essentially you use a hidden Markov model instead of a grammar here. And there it did make a difference. The SVM was more accurate than the Collins. The SVM was more accurate than the Collins perceptron.
You haven't tried it.
I haven't tried it for the parsing, no. Right. Right. So you do just a re-ranking, essentially. Yeah. I mean, you have to have a pretty good base system that's pretty well tuned, so that like the 100 trees that you're re-ranking actually contain a good tree. But so you're kind of starting from a different starting point here. What I find nice about this is that you can actually do the whole problem without any decomposition and different steps in just one big training problem, and you can actually solve that still. From a practical perspective, if you have a good base system that you can be reasonably sure that it gives you a reasonable parse within the top 100, it's probably more efficient to just do the re-ranking. You can do this, I mean, essentially also with the SVM algorithm that I talked about yesterday. Okay, but coming back to the other question from before, what we've done here is essentially we've taken an extremely simple feature space. Essentially, more generally, what we could use as features is any sum of features over the constituents. So, for example, over grammar rules in the tree. And so this small phi here is what we've currently used is just this indicator vector that just has one feature in it. Is it the rule, right? But there's no reason why we should stick with something that simple. What we could use is we could use any feature representation that we could come up with that depends on the rule, where the rule starts, where the rule ends, and any word that occurs in the terminal sequence. So we could have features that are like, I don't know, does the subtree start with while, and does it end with a period? That's a feature that we could put in, whatever. What's the length, the size of the subtree? Does the span of the tree contain the word and? You know, you could come up with all of these features and just throw them at the learning algorithm and let the learning algorithm figure it out, essentially. You would have an extremely hard time training something with these features in a generative way because you have all these dependencies between the features. And I think it would be really hard. So it gives you more expressiveness. So here's one example where we've actually gone this route, not for parsing, but for part of speech tagging, which is just a particular case of parsing, if you want to think about it that way. So we picked the standard Markov model approach, and so we have one state for every tag, and the words are emissions. But now we describe the words not only by the identity of the word, but we describe words by roughly 250,000 features that we just came up. Well, I mean, we don't know anything really about this problem. So what we just came up with is, okay, all word suffixes and prefixes we used as features. Like how long is the word? Was the word capitalized? We just came up with a whole bunch of features, and then just trained this model. And if you think about this, if you wanted to do this in a generative way, you would have to account for dependencies in this 250,000 dimensional vector, which would be hard, especially since like suffix and prefixes have lots of dependencies. They have this subset relation, and it would be very hard. So an MN student did a comparison using standard software that he used in the web, like transformation-based learning, standard implementation of a hidden Markov model tagger, and compared this against a model that's trained in this high-dimensional representation with a structured SVM. Again, we used only a subset of sentences for efficiency reasons here. And you do get, quite a surprising difference in performance. the differences are significant. I don't actually have the error bars, but they are significant.
But now, how does CRFs or MEMS do on that?
Say again. Okay, so this is just a subset, a small subset of the data, right? The full data set, she is better. Yes. I mean, all of these methods would be better on the full data set than this here. So again, we have an efficiency issue here, so we have to work on these algorithms to make it more efficient. Okay, so very briefly, what you would need to do if you wanted to implement, so what I like about this approach is that it's actually very general. And if you want to apply that to a different problem, there are really only three things that you need to do. You have to come up with a loss function. You have to come up with a representation. And for this representation, with an algorithm that computes these argmaxes. And so the software that I've put on the web called svmstruct actually has an API where you essentially just plug these things in, and you can attack a new problem like that. So, and for many of these problems that we're often considering, these problems are essentially already solved, right? Like for Markov models here, the argmax computation is just the Viterbi algorithm. For finite state reducers, again, we have dynamic programming algorithms. For sequence alignment, we have things like Smith-Waterman algorithm, which essentially are just algorithms for solving this argmax for log linear models. So it kind of attaches nicely to the tools that we already have. So I wanted to talk about two more examples, but maybe I'm just going to skip over that. And so we actually have a paper at ICML this year where we use this algorithm to optimize binary text classifiers for F1 score by thinking about this problem as a prediction of a vector. And we also have a paper with Thomas Finley on this noun phrase coreference problem of the kind of learning how to cluster instances. I can show you the one for optimizing F1 score. So this is on a standard benchmark, the Reuters data set, using a standard representation. What I compare is a classification SVM that is trained with just optimizing error rate, so just a straightforward SVM. And I compare this against a structured SVM, where we predict the whole vector at the same time, and it's optimized to minimize F1 loss. And to make sure that I don't bias, that I don't put the regular SVM at a disadvantage, I actually pick the optimal value of C on the test set. So that's kind of giving it a kind of unfair advantage. Still, what you get is, if you look at the test F1 scores, there's a huge difference in terms of the macro average F1 over all the 90 categories. Again, there's an issue in training time. Training time goes way up. So I think one of the pressing problems here is how to make these algorithms faster.
So maybe I'm not fair if you're going to actually get that part of the talk, but so it seems to me the natural way to do this. So right again, I want to go logistic regression, but fortunately in this particular case, you get basically the same thing, right? So instead of thinking about these things as 0-1 classifiers, you think of them as producing
a probability
scores, or whatever you want to call it, whether it's and implicitly giving a ranking. And especially if you have, you use like with the SVMs, you can use John Pass technique to convert your SVM out to probabilities, and then you can figure out how to maximize F1 given those probabilities, right? But that's
right. So if you could actually solve the problem of predicting the probabilities accurately,
yeah,
you would be done.
Tried.
Right.
So,
but it seems like you're trying to solve a really hard problem to solve an easier problem. So, well, I agree. If you could actually predict the probabilities accurately, and I haven't done the experiment here, how well this would work here, for example, using John's method, then yes, you could come up with the optimal threshold, essentially, where to threshold so that you get a good F1 score. But, well,
Or you could just, well, I mean, you don't even, another way to think about it would just, right, you optimize C in hindsight, right? So another option would be to just use some held out data to pick a threshold.
yes, we've done, so another experiment that we've done is we've allowed cost models in here. So we've used an SVM that has a linear cost model, and then we allow tuning the cost model. So essentially, yeah, that means changing the threshold, giving more cost to getting positive examples wrong than negative examples wrong. It shifts the threshold. You can get this up doing that to like 55 point something, but you can't get it up to 61. So essentially what I like about this is that you're formulating your problem. I want a classifier that optimizes F1 score, and then you just solve the problem, essentially. And you don't have to go through multiple steps, first predict probabilities, turn those into classifications. But you can actually solve these problems kind of in one neat step. Mm-hmm.
All of these you've shown as kernelizable.
Yes.
But you won't have to do them once in long feature vectors. So it doesn't sound, have you tried actually using kernel for any of these?
Right. So all of this is kernelizable in the sense that you can use kernels over constituents. So you can still do dynamic programming. In theory, that's possible. In practice, it gets, at least in the implementation that I have, rather slow. So I'm not sure whether it's really, for the problems here, whether it's really worth it. OK, so let me wrap up. So I talked about the problem of predicting complex outputs. And what I think what we have here is a nice and clean framework that is actually rather broadly applicable to many applications. I mean, ranging from parsing to part-of-speech tagging to protein sequence alignment to like predicting, optimizing F1 scores. And the same, and essentially, it's always the same underlying algorithm that can solve these problems with a fairly straightforward API that attaches different parts. So if you're interested in trying this out, the API and implementations for optimizing the F1 score or different other loss functions, for the grammar learning, probably also for the HMM soon, and for the sequence alignment are actually online, so you can download those as software. And again, it's just essentially just a little bit of a plug-in to the general code. I think it's a very interesting area for research. In particular, probably that's one of the questions that you're going to ask. How can you do that with other algorithms beyond SVMs? And I think there's probably similar kinds of general algorithms that you can come up with also for like logistic regression or similar type algorithms too. And I think it would be interesting to essentially take the toolbox that we have for classification and see in how far we can push this for solving these complex prediction problems also with other methods. I think from a practical perspective, one of the most pressing issues is we have a nice, very nice and concise algorithm right now for which we can prove interesting properties, but it's probably not the algorithm that you actually want to use in practice. So thinking about algorithms that actually solve these training problems efficiently for special cases as well. OK, thank you very much.